Okay, so now I want to talk about how are we going to calibrate these models. We talked about fragility functions, vulnerability functions. To think precisely, they all had a set of model parameters in them, right? They had the theta or the beta or the Q and the R or the AX and the B. So anytime we had all those coefficients in the model, where the numerical values for those coefficients come from, okay? And so what we need to do is we need to pick some coefficient values that are representative of the asset that we're studying, right? And there's three general categories I want to talk through in this video of how to calibrate those consequence models. So we can do this empirically with observed data. We can do it analytically using computer simulations or some sort of analysis, or we can use expert opinion. You can use judgment to try to infer these. Those are three specific methods. I drew out a triangle here to say those are all three techniques, but we can, in a particular situation, we can pick on a continuum here, right? So I might do some sort of analysis here that's mostly dependent on analytical methods, but I'm using a little bit of empirical data as well, right? Or I could use some expert opinion based methods, but I'm going to check against empirical data to try to verify what I'm up to. Or I could use some sort of method that's in the middle somewhere. Okay, so there's three methods. So we've got the three approaches. Specific models don't have to exclusively use only one approach or the other. That kind of combinations of these are possible. All right, so that's the concept, but let's talk in a little bit more detail about this. All right, so how would we do this calibration? One method is empirical. And the idea here is we're going to go into the field after earthquakes, and we're going to observe the damage, and we're going to use that to fit a statistical model. All right, so I'll go see in the real world how strong was shaking at different places in the affected zone, and how likely was it for the type of asset that I'm studying to have some level of damage. Okay, as an example of this, I've got shown over on the right, this is some work by Nezrin Basoz and Ann Kermidjan after the Northridge earthquake in California. And they went out and looked at kind of highway overpass bridges, multi-span bridges in California. And they've got plotted here on the horizontal axis, this is peak ground accelerations. And then there's some little symbols. The hollow symbols are observed data. So that little square I pointed to, that's peak ground accelerations of about 0.55 G. And they found that about 75% of the bridges with 0.55 G had minor damage. Okay. And then the little diamond down lower says that about 25% of the bridges had no damage. So the hollow points are this observed damage. And then the statistical model is the filled in points with the lines connecting them. So they fit some functions to this data by seeing what happened across these different levels of peak ground acceleration values. So that's just strictly go get some observed data and fit a model to it. So this has got some really nice advantages. It's very straightforward. I don't have to build any computer models. I don't have to do any experiments or anything like that. I don't have to make very many assumptions either, particularly in contrast to like our analytical methods we'll talk about later, right? It just observes data and fit statistics. I also have built-in validation here, right? So we know that these models represented by these lines are consistent with what happens in the real world because they were fit to observations of what we saw in the real world. Okay. It's also nice for kind of common types of assets. Right, so the figure on the right with these highway overpass bridges, that's good because there was a lot of those bridges in the Los Angeles area where this data was collected from. So it's easy to get a lot of observations. It also works for like residential buildings, particularly if there's a standard type of construction in the area that's being studied. Okay, so lots of good things about this. There are some disadvantages though. So we're going to need a fair amount of data. And if we have common types of assets, that might be possible. A challenge though is we're going to have to put our buildings or our assets into classes, right? So in the figure to the right, all multi-span California bridges went into the same model. You couldn't have a skewed bridge versus a straight bridge or curved bridge or 3-span versus 2-span. You have to lump things together in order to get enough of a sample. Similarly with houses, you can't necessarily do a specific model for 2-story versus 3-story houses or house with a irregularity versus not. If you get too precise with your classes of buildings, you don't have enough data. So you end up having to lump things together. Okay, the next challenge, this one isn't too hard to overcome, but I have to be careful about it. We need unbiased input data. So sometimes when folks go out into the field after an earthquake, they'll look most at the cases where you see damage. And those are the most interesting and the most potential to learn from an engineering perspective. But if people only count the damaged buildings and we don't know how many undamaged buildings or assets there are, we can't figure out the probability of being in a damaged state. And so You have to go out and systematically collect all of the data, including the undamaged assets. So that's important. Another challenge is that we need the horizontal axis value in this plot on the right in order to fit this model. And so we have to know what the intensity measure was at the location of the asset that we observed the damage in. If we've got a ground motion instrument nearby, like really nearby, then that's no problem. We'll just use the instrument. But because the instruments are generally not super dense, that means we've got to go look to instruments that are a little further away from the building. And the ground motion that instrument recorded may not be the shaking intensity that the building experienced. And we have uncertainty in the IM. Recently, there's been new techniques developed to fit these models considering that uncertainty explicitly. And so that's great. But traditionally, people have just tried to either use the closest station as the IM or try to do some sort of like mean estimate of IM and ignore the uncertainty in the IM. And that can lead to uncertainty in the IM showing up as apparent uncertainty in the probability of the damage state. And that can complicate things. Okay, so we can handle it. Typically it was ignored, and it basically led to overestimation of uncertainty in the fragility functions. Okay, so those are some features of this empirical model. The next very common way of calibrating these models is to use, we'll call it analytical methods. And basically, we're going to use a computer model to simulate our consequences. So there's a cartoon here. I've got some kind of figures up top of computer models for some frame buildings that were shaken dynamically. These are nonlinear models that can deteriorate. And so we can simulate them and then observe what level of demands got put into the building. We can infer what level of damage would occur. We know the input ground motion because we did it with an analysis, and then we can link the input ground motions to the outputs. So here's an example with these plots of the top figure is doing these types of analysis with a set of ground motions of increasing intensity. This is called incremental dynamic analysis. That as we head towards the right part of the plot, the intensities are getting larger until the drifts are getting larger and larger in the building, and we infer that a collapse occurred. And then we can count how many collapses occurred as a function of the ground motion intensity. We get the bottom figure, this probability of collapse as a function of IM, and that's a fragility function. The circles are data from computer analyses, and then the line is the fragility function that's fit to this. So there's some advantages to this technique. So first of all, since it's a computer rather than the real world, we can generate the data. It's relatively easy to generate a lot of data. Unlike the real world, where most of our buildings are far away from the rupture and see relatively weaker shaking, maybe only a few are close in and see the strong shaking. In the computer, we can just specify strong shaking. So that's helpful for kind of understanding the severe damage states. We're also not limited to common systems that have a lot of observed data in the field. For example, some of these new high-rise structural systems with like concrete core walls. There's not a lot of them that have been subjected to strong earthquake shaking, so we don't have empirical evidence of how they perform. But in a computer, we can build computer models of those systems and analyze them. We can also put in very specific features of a particular building and get results for that. All right. We also don't have to do this in a vacuum where we're just doing this in an isolated space. We can build computer models of buildings that went through earthquakes. Maybe we have some empirical data about those, and then we can check, do our analytical models produce consistent results with the empirical data? If so, we've got a nice validation. If not, we can study what the discrepancy might be and see if we can resolve that. All right. They're not perfect though, so some disadvantages. All right, we're going to have to make some assumptions. We're having to do some calibration here. We need to make sure that this numerical model actually captures the phenomenon we're trying to study in terms of consequences. So if I'm trying to predict collapse of the building, I better calibrate this numerical model that it actually does collapse in the mechanisms we expect and that it collapses under shaking levels that we see in the real world. There's going to be a bunch of assumptions as well, right? Do we do 2D models or 3D models? Do we have shear failures in the columns or just flexural failures and so on? All the structural engineering assumptions, those are really important to get right if we're going to get realistic predictions of consequences. It's also the case that we have to think carefully about modeling uncertainties here. So a lot of the parameters that need calibration in these models are going to be known only uncertainly. The construction quality of buildings in the real world may or may not match what we've assumed in our computer model. And so tracking those uncertainties are important. Again, that's something that's done carefully in more recent years, but in early days was maybe not considered as carefully. kind of in part because of the above reasons. So this can be time intensive, labor intensive. So building analytical models is not easy. Running all the data, processing all the data, and scrutinizing it, calibrating it, that can be a fair amount of work, particularly relative to the expert opinion that we'll discuss next. So there's some work involved in here. You might argue this is easier than empirical data because we can at least generate the data, whereas in the real world, it's very hard to generate the data. And then also sometimes there's some challenges with kind of how do you communicate out the calibration and modeling uncertainties and things like this? How do you build trust with stakeholders that are using these models? I personally experienced this a bit building these models and say talking to folks in the insurance industry that maybe are used to empirical calibration of their consequence models. How much was the claimed repair costs after earthquakes? And if you come with computer-based models of repair costs, they'll say, oh, this looks all reasonable, but how do I know that these modeled numbers are going to be consistent with what I actually see in the next earthquake? It's depending on the level of conservatism or how critical it is to get these numbers precise. Folks may really have a lot of questions about how the validation and calibration was done. So our third method here, expert opinion. So what we're going to do here is use domain experts that have experience broadly with seeing damage in the field, building computer models, understanding the relative performance of different types of buildings, and trying to then assess what they would predict as being the consequences for some type of building and some level of damage or some level of shaking. Right. As an example of this, ATC 13 is a very famous one. This was from a number of decades ago. 1985 is a report you can go find. And this is an example output from these expert opinion based models for some given building class, just to give you an example. So the key parts of the table here, we've got on the far right side, we've got probability of being in damage as a function of MMI. Maybe let's label that up. Okay, so MMI that's the intensity measure in this case, and that's modified Mercalli intensity. This is a particular scale that's discrete, uses these Roman numerals, so from 6 up to 12 in the headings of that section of the table. Those are ground motion intensities that are increasing. Okay? And then they've got 7 damage states down the rows, kind of indicated in the far left corner. And then we've got kind of probabilities in the table, indicating kind of probabilities of being in a damage state given the MMI. So that's like a fragility function model. And this was based largely on judgment from a set of experts that were convened for this. And they had personal calibration from field experience and things like that. Okay, what's advantageous about this? Right, so first, you don't need much data or analysis. That was particularly important in the 1980s when the computer models for analytical fitting were not really developed yet. There was a lot less field experience with earthquakes, and so we had to stretch what little was known by the experts. And so when you're in a data poor situation, that's helpful, right? There are still data poor situations in the world now, and expert judgment can be useful. It's also really useful for filling in gaps. So I might not prefer to do a pure judgment-based model for kind of all types of buildings, but maybe I've got a lot of data for 1 and 2 story, wood frame buildings, and I want to model for 3-story wood frame buildings. And I don't have as much observational data because there's not as many of those buildings, but I could maybe make a relative assessment of how I think 3-story buildings would perform relative to 1 and 2 story buildings. And so I'm just trying to make a relative adjustment based on expert opinion to fill in that gap without building a whole bunch of computer models or collecting a bunch of field data. So that can be an argument for this. But there are definitely some challenges, as you could probably intuitively guess. So first of all, it's subjective, right? We're just asking experts to make these assessments. And so if those experts are incorrect in their judgment, we've got problems, right? It is possible to calibrate experts or validate experts to some degree. So you can do things like asking for expert opinion models of cases where there is some data to make a comparison against and see how well they do at assessing what's known to be true. Some experts are better at that than others, and so you can pay more attention to those experts. Right. Similarly, when there's multiple experts and they have differing opinions, how are you going to combine those opinions to get an aggregated model? It can be done, but it has to be done carefully, and problems can arise there. Problems that can arise when talking to experts, they can be overconfident. And they may not realize how uncertain they are about situations where they don't have a lot of data to contradict their assumptions. You can also get biased opinions, right? If people only have looked at damaged buildings, they might have some sense that damage is more likely than perhaps it is, things like that. Or, of course, seeing damaged buildings is very impactful emotionally, and that can put a lot of emphasis in your mind on the damaged cases. perhaps relative to other cases that are also likely to occur. Okay, so I think let's stop there. Those are our three general categories of calibration, as well as some thoughts on the utility of each. And again, as we open the video, saying we don't have to use exclusively one or the other. Use expert opinion backed by empirical data or analytical models that are calibrated based on empirical data. And so in reality, we're using all of these, but we want to think about the advantages and disadvantages of each method as we're combining them together.